In this video, I'm going to discuss an interesting problem on colored grids. So suppose that I'm given an n by n grid here, and the cells of these grids are colored as follows. On the diagonal, I have all blue. Above diagonal, I have yellow, and below diagonal, I have red. Okay, so here, for example, 2, 1, I have 2, 1. And as you can see, 2 is larger than 1, so I am below the diagonal and the color is red. If I have something above the diagonal, the color would be yellow. Okay, now at each step, I'm going to swap two rows. Like I'm going to swap this with this. And the next one, I'm going to swap, for example, this with this, and so on and so on. And for each configuration that I would get after swapping, I would look at the colors of the diagonal. And the question is basically asking how many different uh, configuration I would get just for the diagonal. Okay, let me explain this problem with an example here. So here I have a 5 by 5 grid, and I'm going to make swaps step by step just to show you like what the problem is asking, right? So in step 2 here, I'm swapping first and third row. Notice that if I do this swap, I would get this configuration. And so I have this diagonal here. So I basically have red. Let me use a different color here. I have red, I have blue, I have yellow, I have blue and blue. Initially I had all blue, right? 5 blue. Step 3, I'm going to swap this one, right, with this one. So 3 and 4 are swapped, and that would result in this configuration. And so here I have red, blue, red, yellow, blue. And so for the next one, this is not changed, this is not changed, not changed. And here, oh, okay, here I should not have included this because this seems, no. Here I have 3 here. I have this one is swapped with this one, exactly. So 1 and 3 are swapped. And so the resulting configuration for the diagonal is red, blue, blue, yellow, blue. And you can see like so many different steps here. I'm not going to write the configuration, the resulting diagonal for all of them, but you can see the idea of this question and what exactly it's asking. So here I have all 5B. I have RB, Y, BB, RB, R, Y, B, and so on. So the question is asking how many different sequence I get, right? So the question is basically asking us question how many different diagonal configuration, let's call this configuration, or arrangement. Arrangement may be a better word here. Arrangement we may obtain using, like, not using, perhaps applying, so by applying row swaps. Okay, so Let me actually give a simpler example. Like consider 4 by 4. This is a 4 by 4. And initially I have all the blue ones here, correct? And now I'm going to make a swap with the first and second. So it would become like this. Then I'm going to make a swap with like the second one and third one. I would get this, right? So I can construct different arrangements by just making the swaps. But notice that here, this is something very important, that I'm not actually bothering with the colors. I just keep track of the blue cells inside each row. Each row has a unique blue cell in it. And so there are 4 blue cells and 1 in each row, and that would actually give me the configuration. Remember that above the line I had yellow, and above the diagonal I have yellow, and below the diagonal I have red. So here, for example, here I have blue, 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 but here, because this one is below the diagonal, right? This is from the second row. So this is red, red. And this is above the diagonal because this is from first row. So I have yellow and then blue, blue. And the same for this one. This is below the diagonal red, then also below the diagonal for here, R, and then here I have above the diagonal yellow, and I have blue. All right? So I actually don't bother with the colors anymore. I just pay attention to where the blue cells is, and I can figure out the color of this cell in the diagonal cell. If it's on the left-hand side, it must be red. If it's on the right-hand side, it must be yellow. Sounds good. Okay, this was the first observation. The second observation is that I'm going to think about this sort of configuration as something called permutation. Permutation. Why is that? What is a permutation? Permutation is suppose that you are given a set or you are given a set. So an example, easiest to just explain it by way of an example. So suppose that you have a set 1, 2, 3, 4. What is a permutation of it? A permutation is just it's just a shuffle of these 4 numbers. So if I write 4, 1, 2, 3, this is a permutation. Or if I write 1, 4, 3, 2, another permutation. But if I write 1, 1, 2, 3, this is not a permutation. Okay? This is not a permutation. That's because 4 is not here. So basically just a shuffle of all these 4 values. So the order is different because we are shuffling, but we do have the numbers 1 to 4 uh, by definition. And we all know that the number of permutation on 1 to n is equal to n factorial, which is by definition n times n minus 1 times 1. So number of permutation on the set 1, 2, 3, 4 is equal to 4 times 3 times 2 times 1, which is 24. Okay, so now why exactly we have a one-to-one correspondence between this configuration or arrangement and permutation? So here I have like just look at the location of the blue cell here. 1, 2, 3, 4, right? But here is 2, 1, 3, 4. And here I have 2, 3. Uh, I might have made a mistake here because I have 2 again. So this cannot be correct. I have changed. So this must be the first one. This must be the first one. And I have 2, 3, 1, 4. So basically each permutation gives us a location of the blue cells, and the location of the blue cells would give me this coloring that I have for the diagonal. So I have 1, 2, 3, 4, 2, 1, 3, 4, 2, 3, 1, 4. As another important observation is that this way, by just swapping the rows, I can achieve any possible permutation, right? This is very fundamental, and just write it down. Fact: by row swaps. So let me just write row swaps here. Row swaps gives all the permutation, all the possible permutation. Permutation, which are n factorial. So we do have the n factorial permutation using row swaps. And the reason for it, this is like a straightforward classic fact in mathematics. But the reason for it is just consider a permutation. Let me just give you an example. Like 1, like 5, 1, 3, 4, 2. This is a permutation of number 1 to 5, right? The set of 5 elements. How can I achieve this specific permutation using swaps? Okay, the idea is swap 5 with 1 and then swap the second element with third element and third element with fourth element and then fourth element with the last element. If I do that, I would get 1, 5, 3, 4, 2. Then I get 1, 3, 5, 4, 2. Then I get 1, 3, 4, 5, 2. Then I get 1, 3, 4, 2, 5. Okay, so 5 is back to its original place here. Notice that here I started with 1, 2, 3, 4, 5. Now do the same trick for here. Swap 4 with 2 and get 1, 3, 2, 4, 5. Then swap 3 with 2, get 1, 2, 3, 4, 5. Notice that just by swapping, you can bring each element to its original position, which was 1, 2, 3, 4, 5. This is like the starting setting, right? This is the starting arrangement. We can go from the starting arrangement to any arbitrary arrangement by just swapping. That basically is saying, okay, we can achieve all permutation using just row swaps. But notice, there is a very important catch here. This problem is not just about counting the number of permutation, because we do have n factorial permutation. The point is, some of these permutation produce the same arrangements for the diagonal. For example, here, notice that here I have red, red, yellow, 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 and here I have red, red, yellow, yellow, yellow. But notice that these two are not the same. So if I write step 9, I would get 5, 4, 2, 1, 3. If I write a step 10, I would get 5, 4, 2, 3, 1. These two permutations are not the same, but in terms of coloring for the diagonal, they produce the same thing. Okay? Sounds good. Now we get the idea of what exactly this problem is asking. So we consider all the possible permutation, and then each permutation produces some arrangement for the diagonal. And from there, we should actually find out how many different arrangement we get this way. Okay, so from now on, we basically can forget about swapping. Swapping here is not relevant anymore. We just think about the all possible permutation, and then each permutation produces a specific configuration, a specific arrangement for the diagonal, and from there, we want to see how many different arrangements we get. Okay, sounds good. Now, one very fundamental observation. Fundamental observation. Suppose we have a, like, suppose I have a 5 by 5 grid. Okay, now think about like the first one is blue, so suppose that the first one is blue, and then the second one is not blue. It's here I must have yellow because 1 3 I get 1 3 1 3, so this is red, right? This is below the line because it's on the left hand side. Initially it was here, so this column is this one, this cell is this one, so it's red, right? So I have red here. Then the next one is, let's say, I cannot have here anymore because the third row is actually placed here. So I get 1, I get 3, then assume I get 5, so I have here. Assume I get 2, I have here. Then assume I get 4, I have here. And actually this is not, so notice that here I get R first. So I have blue and then R and then R, 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 right? The point I'm trying to make, let me actually do another example. Let me remove this and go with another example. Here, suppose that I am given like 2 here, and then I have 5, I have 4. So what are the colors here? I have red here, I have yellow here, I have again red, and I have yellow. Notice that R comes first and yellow comes last. That's the fundamental observation. So if I just look at the diagonal, if I just look at the diagonal and try to write it inside like a column, this would be size n, okay? Then what exactly this column look like? This is the diagonal that I just bring it here, right? And make it like a vertical, just for simplification. So here, for example, I have a 5, 1, 2, 3, 4, 5, and I have red, I have, sorry, black, blue, and then I have red, I have yellow, I have red, I have yellow. So, and the argument I made is like the first, if you look from north, from top, the first not blue cell must be red. Okay, let me write it from top. The first not blue cell is red. From bottom, the first not blue cell is yellow. Why that's true? Okay, let me just show the first argument. The second argument follows immediately. It's similarly, all right? So I have something like, so this is the grid I have. 5 by 5, and I have this, blue, blue, and here I have something not blue. And the question is this red or why? Is this red or yellow? And notice that I've already used 1 and 2, and the third one, assuming that it's not 3, is either 4 or 5. It cannot be less than 3, right? Because I've already used 1 and 2. If it's not less than 3 and it's either 4 or 5, actually I have one column less here. 1, 2. If it's either 4 or 5, that basically means it's either here or here. So the blue cell is either here or here. And that basically means this is either way, this is below the line. And this must be red, right? And the same argument works if you look in this direction. The first not blue one, if it's like, let's say this is 5, and if it's not 4, it's either 3 or 2 or 1, 3, 2 or 1, and either way, this would be on the right-hand side of this blue cell, so this must be yellow. Sounds good? Okay, so basically I showed that the first not blue cell is red and the first not blue cell from the bottom is yellow. So we have shown that from top, the first not blue cell is red, and also from bottom, the first not blue cell is yellow. So let me call just the definition and arrangement for the diagonal, right? For the diagonal is called valid if it satisfies the above two conditions. So we have shown that any arrangement we get by way of row swaps is valid. Okay, and is valid, then I'm going to claim that claim. Any valid arrangement is possible for any valid arrangement is attainable for some permutation which was equivalent to row swaps that I discussed, or row swap for some permutation or row swaps. Okay, if I prove the claim, then I just need to count the number of valid arrangement uh, for my basically 1 to n. So the number of valid arrangement for a value is between 1 to n. The number of valid permutation basically, thus the answer would be the number of permutation. Note that I'm using the term permutation, row swaps, arrangement interchangeably. And because as I discussed before, all of these are equivalent. All right, so now I'm going to make an important observation here. Let me go here. The observation is it suffices to count the number of valid permutation on numbers on, let's say, set, on the set, on the set 1 to n minus k. Why this is true? So let me explain by an example. Suppose that I have 4, 1, 3, 2. So n is 4 here. And this is equivalent to, oh, sorry, on the set n 1 to minus k, which does not have any blue cell. Okay, so here n is equal to 4 and I have one blue set at 3, at location 3. Then this is basically the same as this arrangement for n equal to 3, but there is a small change here. 3, 1, 2. There is no blue cell here, and I just work with n equal to 3. And what happened exactly? Anything above 3 is deducted by like value 1, like 4 has become 3. Anything below 3 has remained the same. So 2 is 2 and 1 is 1. So feel free to spend some time thinking about it, that I can just do the counting when there are no blue cells. And if there are like k blue cells, then I just need to do the find a valid permutation with no blue cell for 1 to n minus k. Okay, so and the answer would be, finally the answer would be like sum of like n choose k times number of valid permutation on 1 to n minus k with no blue cell. Okay, and k would vary from 0 to n minus 2, and the whole thing would be n plus 1. Why? This is correspondence, 1 plus 1 corresponds to all blue arrangement. And the reason that it goes to n minus 2 is because if I have n minus 1 blue cell, the last one must be blue as well. So, right, this is obvious. I cannot have like just n minus 1 blue cell. If n minus 1 uh, n minus 1 values are like 1 to, if 1 to, for example, 1 to n minus 1 or 1 to n minus 1, the last one must be n as well. Okay, so that's why n minus 2, I put n minus 2 here. So there you go. Now I need to count the number of valid permutation on the set 1 minus 1 to n minus k with no blue cell, and I also need to show that all of these valid permutation is attainable by way of some permutation. Okay, to see that, let's just consider a valid permutation start with r. So I have r till I get to some y, and then I repeat this, right? Notice that there is no there are no blue cells, so I just have R and Y. And so there is an R block, then there is a Y block, then there is an R block, and it continues, right? Because at the end I must end with Y. So I am like sure. I mean, I know that uh, if I consider this as a block here, so this is call it the block RY, then I would have block RY, block RY, till block RY. So the entire arrangement consists of a bunch of block RY. And if this is A and this is B, then this is block RY, A and B. Okay, so here I have A1, B1, I have A2, B2, and I have let's say, T, BT. Okay, and sum of AI plus sum of BI is the sum of all the numbers that I have, n minus k, let's say. Because as I assume that I had like k blue cells, so the number, the elements left are a minus k, of size a minus k. So basically now here I just need to show that this guy here with just one block is attainable. And I can repeat the thing for repeating the same argument for the rest of them. I just need to augment shift all the values that I have here. Okay, so let's consider this permutation. Let's consider uh, B1 plus 1, B1 plus A1, and then 1, B1. Okay, I have used the values inside this set, 1, 2, till A1 plus B1, and this corresponds to R, until here, then Y, Y, right? And this basically shows that I can attain this block, and the same argument goes for the rest of them. In fact, notice that B1 plus 1 is larger than 1, and B1 plus A1 is also larger than A1. So all of these things would lie like on the left-hand side of the blue cell, corresponding blue cell. So there must be red. And the same for here. This is less than B1. This is less than A1 plus 1, and this is less than A1 plus B1. So all of them lies on the right-hand side of the blue cell, the corresponding cell for B1 or 1, or everything here. And then, so I should have Y, Y for this block. And that's it. So that's, I have achieved this block. If I want to do, if I want to repeat it for the same, I want to repeat the same argument for the next block, I can write B1 plus 1. I shift everything by A1 plus B1, right? Sorry, here I should have B2 plus 1. Then B2 plus A2 plus A1 plus B1. Then I should here start with A1 plus B1, 1 plus A1 plus B1 till B2 plus A1 plus B1. So shift everything by A1 plus B1. And that's it. That basically shows that this column is attainable by this permutation, and all this column is attainable by a combination of all this permutation I just showed you put together. So I just need to go back and compute the sum that I showed you, right? I can compute, I need to compute this sum. And so what's the number of valid permutation on 1 to n minus, on the set 1 to n minus k? The only restriction was the first one to be r, the last one to be n. So this number here is equal to 2 to the power n minus k minus 2, right? So the final answer is 1 plus sum of k from 0 to n minus 2 n choose k times 2 to the power n minus k minus 2. And this is 1 plus 1 over 4. This is the binomial. This is just the binomial, right? Sum of k from n choose k, 2 to the power n minus k, k from 0 to n minus 2. And this is equal to 1 plus 1 divided by 4 times 3 to the power n minus the two terms that I'm missing. For n, I would get 1. For n minus 1, I would get n times 2n, or basically I should just write 2n. And I have 2n here. And this is the final answer. If you have this answer, your solution is correct. And that was the complete proof for this question. Feel free to ask me any question and I will try to respond as soon as possible. Thank you so much for watching.